Okay, let's dive into this. Welcome to today's explainer. You know, we're taking seemingly impenetrable academic concepts and making them, well, remarkably clear and accessible. Today, we're tackling a highly specific scientific document, and we're going to deconstruct it together, piece by piece. We're looking at a fundamental process that literally changed the face of chemistry and biology. It's a technique known as chromatography. I know, it sounds kind of intimidating, but I promise you the logic behind it is absolutely brilliant. Imagine you're handed a complex puzzle, right? But all the pieces are completely blended together into a single uniform substance. So what happens when you need to separate the inseparable? How do you take a chemical mixture and pull it apart to reveal the hidden components inside? Well, that is the exact problem scientists face all the time. And chromatography? It's the ultimate solution. It acts like a key, unlocking these tightly bound mixtures. Here's the foundational source text we're tackling today. Now, at first glance, yeah, it's packed with academic jargon, overlapping definitions, and that super clinical formatting. It's exactly the kind of text that might normally make you want to just close the book and walk away. But hey, don't worry, because we're going to meticulously break down this intimidating jargon together. By the end of this explainer, every single word on this page is going to make perfect sense to you. First up, let's look at the three core goals of chromatography. The text breaks down the objective into three primary action verbs: separate, identify, and purify. Think of this as a sequence. First, you pull the mixture apart. You separate it. Simple enough. Once those hidden pieces are revealed, you can figure out what they actually are. You identify them. And finally, if you want to isolate a specific component without any contamination from the others, you extract it cleanly. You purify it. Whether your final goal is separation, identification, or purification, the foundational mechanics of the whole shebang remain exactly the same. And here's the exact quote from the top of our source document validating those goals. Chromatography is a separation technique used to separate, identify, and purify the components of a mixture. This tells us exactly what this tool is built to accomplish, right before we even begin to unpack the complex physics of how it actually does it. So, we've established the what and the why. Now it's time for decoding the jargon. Now, what's really interesting here is how the document finishes that first definition. It says, based on their differential distribution between a stationary phase and a mobile phase. Okay, pause. The phrase differential distribution sounds incredibly complicated, doesn't it? But it's actually describing a very intuitive physical behavior. Let's isolate that specific term for a second. By translating the text, we can define differential distribution as simply the way components of a mixture are shared or spread out differently between phases. Imagine a group of people walking through a really crowded market. Some folks are going to stop frequently to look at the stalls, while others will just walk straight through without pausing, right? They're distributing themselves differently based on how they interact with their environment. That is exactly what the components of a chemical mixture are doing here. But, this distribution doesn't just happen in a vacuum. It requires two distinct interacting environments to work: a stationary phase and a mobile phase. It's a real push and pull. One stays completely still while the other is actively moving. Now, if you read further down our source document, the author actually provides a second definition. Chromatography is the process of separating components of a mixture by allowing them to move at different rates. And this brilliantly illustrates how the text itself simplifies the previous academic jargon. The concept of differential distribution is suddenly grounded in a much more visual idea. Things are simply moving at different speeds. So these two definitions, differential distribution and moving at different rates, they're just two different ways of stating the exact same mechanical truth. Because components interact differently with their environment, they end up traveling at different speeds, naturally separating over time. To really understand the physical mechanics, we've got to look at the engine of it all, the stationary and mobile phases. The second definition from our text spells out this push and pull relationship perfectly. The components are moving through a stationary phase, but they're doing so under the influence of a mobile phase. Think of it like this. The active mobile phase acts as a vehicle, driving the mixture forward, while the static environment of the stationary phase acts as an obstacle course, slowing down certain components more than others. Of course, science doesn't just appear out of nowhere, right? It's discovered by people. Let's look at the historical origins. 1906, over a century ago. Long before modern computers or advanced laboratory robotics, the foundation for separating the inseparable was laid down. The document identifies the creator of this technique is the Russian botanist Mikhail Twet. And what is particularly fascinating here is his background. He wasn't a theoretical physicist. He was a botanist. He was out there studying plants. This fact roots these clinical, highly technical scientific terms we just learned, like mobile phase and differential distribution, firmly in the study of the natural world. Actually, he developed this technique originally just to separate plant pigments. As you can see, Mikhail Twet and the year 1906 are immortalized right at the bottom of our source text, bringing our explainer full circle. We started out deciphering complex academic rules and worked our way all the way down to an incredible human discovery. We've seen how pushing a mixture through a stationary environment allows us to literally identify the invisible building blocks of matter, which leads us to a fascinating final thought. If a mobile phase can reveal the hidden components of a simple mixture, what else in our world is just waiting to be separated and identified? Think about the massive implications of this tool across medicine, environmental science, and beyond. The power to separate the inseparable is nothing short of revolutionary. Thank you so much for joining me for this explainer, and hey, keep questioning what's hidden inside the world around you.